Carboxylic acids are weak acids. We can use pKa to quantify how strong or weak an acid is, and we can use pH and pKa to tell us the charge of an acid. This is important when looking at amino acids and proteins. Acids are found almost everywhere. The sting from an ant bite is from formic acid. The smell of vinegar is from acetic acid. The sour taste from lemons is from citric acid. And saturated fats and unsaturated fats are also acids. Arachidonic acid is found in every cell in our body, and when we are injured, the arachidonic acid is converted to prostaglandins, which are involved in inflammation and pain. Ibuprofen inhibits the cyclooxygenase or COX enzyme, and that prevents the formation of prostaglandins, which will relieve pain and reduce inflammation. Olive oil also blocks that COX enzyme. Resveratrol is another compound that blocks the COX enzyme, so perhaps this is a good reason for drinking red wine. Inflammation is bad for our body, and our body uses these resolvent compounds to reduce inflammation. Omega-3 fatty acids are used to make these resolvent compounds, and omega-3 fatty acid has an alkene group on the third carbon from the end. This protectant compound, which helps fight the flu, is also an omega-3 fatty acid. We've looked at different ways to make acids, so stop the video and identify the reaction conditions for each reaction. So here are the conditions. Note that many of the reactions to produce an acid are oxidation reactions. Although carboxylic acids are weak acids, some organic acids are stronger than others, so stop the video and rank the acids from strongest to weakest. So here are the answers. So the lower the pKa, the stronger the acid. So here's the ranking. If you don't happen to have a pKa table, remember that the stronger acid has the weaker or more stable conjugate base. So this compound is the most stable conjugate base, which comes from the strongest acid. That compound is the least stable conjugate base, which means the weakest acid. Note also we can draw resonance structures for these three conjugate bases, but not for that one. In biology, the pH determines the charge on an amino acid and protein. We can determine the charge by looking at the pH and pKa of that acid. So let's do an example. Acetic acid has a pKa of 4.7, so at low pH, the solution contains almost entirely acetic acid molecules, which has a charge of 0. As the pH increases, that is, as we remove H plus ions, the reaction shifts toward the product side and more acetate ion forms. Remember that from Le Chatelier's principle. When the pH equals the pKa, in this case 4.7, there's going to be an equal amount of acetic acid and acetate ions. So the charge at pH 4.7 will be half 0 and half minus 1. As the pH continues to increase, the solution will contain almost all acetate ions, and the charge on the solution will be minus 1. So the charge on acetic acid at pH 3 is going to be 0, and at pH 9, the charge is going to be minus 1. Let's apply the pH, pKa, and charge ideas to glycine. So stop the video and answer these questions. So glycine can donate 2 protons. The proton which is donated first is this one. Remember that the lower the pKa, the stronger the acid. That's the one that's donated first. The glycine titration curve will help us answer the remaining questions. So at low pH, this is the form of glycine which has a charge of plus 1. As the pH increases, this proton is removed and this form of glycine forms, which has a charge of 0. And at high pH, this proton is removed to form this form of glycine, which has a charge of minus 1. So at pH 2, the charge is going to be plus 1. At physiological pH of 7.4, that's around here, it will be, the form will be 0 and minus 1. The pi of glycine, which is the isoelectric point where the charge equals 0, that'll leave this point here, the first endpoint, so that'll be a pH of about 6.06, which we can calculate using this equation. And the buffer regions are the flat regions in the titration curve, and that's around the pKa, so that'll be about 2.35 and 9.78. We can use pH and charge to explain how a toxic protein interacts with a non-toxic protein. So at low pH, these two amino acid residues in the toxic protein would be protonated, and that promotes association with the non-toxic protein, perhaps by ionic bonding. At physiological pH, those amino acid residues would be deprotonated, allowing release of the toxic protein from the non-toxic protein. So in that case, the charge on the toxic protein would be either low or zero,